All right, Keith, you're going to be live in like 10 seconds.
That's fine. I got 10
Okay,
seconds.
you're live.
I'm live? All right. He is. He is. At least for another, what is that, hour and 2 minutes or whatever. Anyway, 52 minutes. Okay, anyway, regardless, welcome Los Angeles Astronomical Society to your October 20th, 2025 general meeting. Give yourself a round of applause. You're in the Leonard Nimoy Amphitheater at Griffith Park Observatory. And I'm actually really looking forward to the speaker. We have some governance. You guys are going to be voting on the future of the club. It's really stressful. I hope you guys read your ballots. It's our big, beautiful bylaws that we're going to be voting on. Actually, I was working on that for a while on the way up here. I know. Thanks. Okay, then we're going to do some announcements. Then I'm going to announce the Good Heavens winner acknowledgement for the month. Then we're going to give away some door prizes. Then I'm going to tell you what your future could be if you show up again, like you did tonight. And then we're going to go home. So, as is tradition, we like to out the new members. So make yourself known so I can run up and you can tell me something that we'll believe that you say. What do we got? Good enough. What's your name?
Joe.
Excellent. What brought you to the Los Angeles Astronomical Society?
Well, I was talking to Jeff at a dinner party, and he
That's great.
haha, and he told me about it, and now I am here.
Awesome. Thank you very much. Anyone else? Yes. We were also talking to Jeff at a dinner party.
No, I was talking to Zach.
Great.
Thank you.
Excellent. And what brought you into the club?
Uh,
No, I know, but like, for yourself,
oh,
other than companionship.
space is cool. Yeah.
It is. It's really cool. Awesome. Well, this is the place for space, but that's another club's motto, but it is also a place for space. Oh, okay.
Hi, I'm Bailey. I'm new.
Awesome. To the Earth? To the club.
Yes.
All right, awesome. Well, welcome. Welcome. All right. We got more? Oh, man. All right. I'm going to introduce Khan. I know this guy already. I feel like he is like my brother from another continent. This guy... Oh, he was in Astro Trip. This guy and I nearly shared a bedroom. All right, out with it.
I'm Ken. So really nice to meet you guys. So I just attended the Astro Trip third. Yeah. So we just coming back from Amber Crater this morning. Oh, the traffic is driving me crazy. Yeah, and we got a lot of image from that. It's a really dark night, and the guys have a hiking. It's really crazy, I would say. During the midnight, 3 hours during the midnight is really crazy. Yeah. Well, anyways, I would like to maybe learn from others. So because I focus on the shooting only. So yeah, I try to learn some like visual things. Yeah, to use my telescope. I'm not sure if my telescope can be used as visual things. So yeah, thank you.
We'll find out. He actually has been helping me out, learning a little bit about astrophotography. He's a super great guy. Good sense of humor. Go get him attitude. All things we value. What about in Zoomland? That was wait till I come all the way down. That's malicious. Stay right there. Don't you move. I have a lot of power, I can end you. Okay.
Hello.
What's your name?
I'm Nick.
Hi, Nick. What brought you to Los Angeles Astronomical Society?
One of the guests here, one of my friends.
Is it also Jeff?
It is.
I knew it. Did you talk to him at a dinner party?
Yeah.
Oh, God, that's a great dinner party. That's amazing. I know. We actually got to officially promote. What's going on at this dinner party, Jeff? Different dinner party. He's doing better than our outreach. Holy crap.
Yeah, commission's in order, yeah.
Fair enough. All right. Well, welcome. We're doing our best. We're setting up next to restaurants, and we'll actually start a restaurant. We're going to start the Los Angeles Culinary Society. All right. Let's see. Do we have anybody in Zoom land that wants to identify themselves as new? Although I don't think I see any. I think I know all of you. Oh, we got one. All right, Sergio, unmute yourself.
Yeah, my name is Sergio. Excited to be a part of this. I do not know Jeff. Looking forward to knowing Jeff. Maybe at a dinner party.
I'll tell you what. I'm kind of hungry. You got a dinner party after this? We should. Anyway, sorry, Sergio. Keep going.
No, that's it. Been a huge fan of astronomy. Grew up down the street from Caltech. Went to a lot of different lectures out there. Thought it was about time to join a group of people with like-minded, neck problems. And since we're always looking up, and that's about it. Very excited to be here.
Awesome. Thank you very much for joining. Okay, that was excellent. That was a lot of fun. It was a good group. This feels like bleachers. Could you guys do like a wave or something? No, that's all right. Start on one side, work your way over. There we go. All right, we got our. You think Zoom people did actually work? They did it, guys. They did it. That was awesome. Okay. All right. I think it is time to introduce the introducer to our guest speaker. And with no further ado, Laura May Abron.
Hello. Sorry I'm not here. I'm still at the Grand Canyon, but very excited for our speaker tonight. I originally met her in 2023 at the ACM. For those of you who don't know this is a very, very big conference. It's the Asteroids, Comets, and Meteor conference, and it occurred in Flagstaff. And so I met the fantastic Dr. Elizabeth A. Silber at a Super Bolides workshop. She is a senior R&D scientist at Sandia National Laboratories and an adjunct research professor at Western University in Canada. She has authored over 100 publications and delivered more than 200 scientific presentations in the fields of meteor and impact physics, shockwave dynamics, and infrasound sensing. Her research focuses on natural and artificial atmospheric entry phenomena, including meteoroid impact, spacecraft reentries, and explosive source characterization. She has led or co-led several observation campaigns, including the 2023 OSIRIS-REx Sample Return Capsule re-entry effort, which I was very disappointed I couldn't go to. She invited me. They went up to the north of California, and they were able to get data on this. It was a pretty big thing. And she serves on the editorial board for Nature Scientific Reports. So go ahead and take it away.
Thank you so very much. Good evening, everyone. It's a real pleasure to be here. I want to start by extending a heartfelt thank you to Laura May and everyone at the Los Angeles Astronomical Society for the generous invitation to speak with you tonight. So I will share my screen and shut off my video just in case there are issues with sound. Are you able to see my presentation?
Yes.
Wonderful. Thank you. So once again, good evening, everyone. Tonight, we will explore the hidden world of sound. We're going on a journey into the science of infrasound, listening to everything from natural meteoroid entries to the controlled re-entries of spacecraft returning home. So look at this beautiful image. Many of you have probably seen something like this yourselves, a meteor shower, a shooting star streaking across the night sky. We make wishes on them. We admire their fleeting beauty. But have you ever stopped to think about what they sound like? Of course, we can't hear them with our own ears. They're too high, too far away. But what if I told you there's a way to listen to these events? What if I told you that our atmosphere is filled with a symphony of inaudible sounds, deep, low-frequency waves that carry the stories of some of the most powerful events on Earth and above it? So here's our roadmap for the evening. We'll start with some basics of what infrasound is and how we measure it. Then we'll look at nature's fireworks, meteoroid entries, and see how infrasound helps us understand these unpredictable visitors. We'll touch on some major historical events that shape the field, and then we'll discuss how we use controlled spacecraft reentries, like NASA's recent OSIRIS-REx mission, as perfect experiments to test our hypothesis. And finally, we'll talk about why all of this matters, from atmospheric science to the very real topic of planetary defense. So what exactly is infrasound? Think of it like this. Just as there are colors our eyes can't see, like infrared or ultraviolet, there are sounds our ears can't hear. The sound spectrum on this slide shows range of human hearing. Anything above, it's called ultrasound. This, you can think of it, dog whistles or medical imaging. And everything below it, usually below 20 hertz, although some people have better sensitivity and can hear sounds as low as 16 hertz, that's called infrasound. It's a sound so deep, so low, that it's completely inaudible to us. And as you can see from this diagram, our planet is humming with it. There are natural sources like volcanoes, storms, and of course meteors, and there are human-made or anthropogenic sources like explosions, mining activity, rocket launches, and aircraft. Now, what makes infrasound so special? Well, two things. It has a very low wavelength, and it loses very little energy, or in other words, attenuates very slowly as it travels. That means that sound from a massive explosion or a meteor airburst can travel hundreds or even thousands of kilometers around the globe, carrying vital information about the event that created it. So, to interpret these silent signals, we look at two main characteristics. One is the signal's period, and the other one is the amplitude. So what is shown here is the classic N-wave shape. This is what you can call a textbook example of a signal associated with a shock wave. So we see that initial sharp rise, which is compression of the atmosphere or the overpressure. This is followed by a negative phase or rarefaction, where the pressure drops below the ambient level. The amplitude is the height of that initial peak and tells us how intense the pressure wave is. Think of it as the loudness of the event. The period is essentially the duration of the signal, or one cycle, or the time between repeating features. That gives us clues about the size and time scale of these energy releases. This particular graph is a cornerstone of our field. It shows the important relationship between the signal's period and the energy of the source. So on the bottom axis, we have the period in seconds, and on the vertical axis, we have energy released measured in kilotons of TNT equivalent. The period energy relations for bolides were first published by Doug Revell of Los Alamos in 1997, and then refined over time to reflect a larger population of bolide events. Hence, you see the multiple lines. But the takeaway is as follows. The longer the period, the higher the energy. So why is this? A more energetic event, like a larger meteoroid airburst, creates a physically larger zone of shockwave generation in the atmosphere. So this larger source region naturally produces a longer wavelength, and thus a longer period, in the resulting sound wave. So a longer period can also indicate the event happened at a higher altitude, where the air is thinner, allowing the shockwave to expand more. So it's a diagnostic. So when it comes to amplitude or the signal strength, in an ideal case, and we never deal with ideal cases, a higher amplitude signal is a more powerful concentrated energy release, perhaps closer to the sensor or at a lower altitude. But when we talk about energy relationship, the infrasound wave is a direct proxy for the event's energy being deposited into the atmosphere. So the signal's amplitude or loudness is directly related to the strength of that energy release at the source. So more powerful event deposits more energy, creates a stronger shock wave, and therefore results in a higher amplitude signal. However, it's not quite that simple. The amplitude we measure also decreases as the wave travels, spreading over a distance, and it's affected by the altitude of the source. And as I mentioned, real-world signals are rarely clean. So we can see two examples here. In one, we can readily see the signal one on top, but in the bottom plot, it's a bit more difficult to do so. So signals can be complex, sometimes very faint and elusive, buried in the background noise of the Earth. So this requires analysts to apply a whole toolkit of advanced signal processing techniques to isolate and derive meaningful information from the data. And in many occasions, we actually can't even see anything because noise can dominate the signal. So how do these sound waves travel so far? Well, our atmosphere is not just a uniform block of air. As you can see in the temperature profile on the right, it's layered. These layers with their different temperatures and densities act like channels or ducts. This is depicted in the plot below, which shows infrasound rays taking different propagation paths through the atmosphere. So these infrasound waves can get trapped in the ducts and propagate for very long distances, bouncing between atmospheric layer like sound in a hallway. And that's why it can propagate over long distances. And things can get even more complex. Winds also play a huge role, especially high altitude winds that change with seasons. As shown in this plot, we see east, west, and north-south components that change according to season. So we have to account for these winds to accurately trace a signal back to its source. It's like trying to hear someone shouting across a windy field. You have to know which way the wind is blowing. This chart gives you an idea of different infrasound signatures. You can see that different phenomena tend to produce waves with different characteristic periods. However, many of the sources overlap. A signal with a 1 second period could be a bolide, an earthquake, or a human-made explosion. So this ambiguity is a key challenge in infrasound analysis. And it's why context data from multiple stations are so important for correctly identifying the event. So why go to all this trouble? Why do we care? Well, infrasound sensors like the one you see here are relatively cheap and passive. So then that means they just listen and they work 24/7, regardless of clouds, daylight, or weather. This makes them the perfect sentinels for a global monitoring system, listening for transient, high-energy events anywhere on the planet, whether it's the rumble of a distant volcanic eruption, the acoustic signature of a lightning strike, or, as we'll focus on tonight, the shock wave from a meteor entering our atmosphere. Now, let's turn to one of the most exciting natural sources, meteoroids. These are visitors from space, fragments of asteroids and comets. They slam into our atmosphere at mind-boggling speeds, anywhere from 11.2 to over 72 kilometers per second. That's a range of roughly 25,000 to 162,000 miles per hour. That incredible speed means they carry tremendous kinetic energy, which is released as an explosive combination of heat, light, and powerful shock waves. But before we continue, just a quick clarification on terms, which I'm sure this audience knows well. When in space, it's a meteoroid. The streak of light we see is the meteor. If that meteor is exceptionally bright, brighter than planet Venus, we call it a fireball. If that fireball explodes in the atmosphere, it's often called a bolide. For our purposes tonight, I'll be using terms fireball and bolide and meteor more or less interchangeably to refer to these large, bright events. And of course, if a piece survives the journey to the ground, it becomes a meteorite. So, as a meteoroid blazes through the atmosphere, it violently compresses the air in front of it, creating a shock wave. This is the source of infrasound. When that shock wave decays to acoustic spectrum, it becomes sound and can propagate over long distances. This process also generates an intense flash of light, and brightness of that light over time gives us what's called a light curve. And that light curve, depending on features we see in meteoroid, whether we have fragmentation or no fragmentation, that light curve carries signatures of light fluctuations over time, and that is also reflected in the infrasound signals we see. If the meteoroid stays intact, it will produce a single smooth peak in its light curve. But if it fragments, you get multiple peaks. And here's some different ways that can happen. An intact body will create what we call a cylindrical line source shock wave that is shown in the upper left. This just means that the shock wave is generated continuously along the object's long linear path through the atmosphere, like the wake of a boat, but in 3 dimensions. This often produces that clean N wave shape in infrasound. But continuous fragmentation, multiple breakup episodes, or a final massive airburst all produce unique infrasound signatures that carry clues about the object's energy and fragmentation behavior. Of course, we do not rely on infrasound alone. We combine it with other tools, especially all-sky camera networks. By using cameras from different vantage points, we can triangulate the meteor's position in the sky, and this allows us to reconstruct its 3D trajectory, calculate its velocity, and then we can feed that information into our models to know exactly where to listen for the infrasound signal and when. The infrasound, in turn, provides that important layer of information about the energy release, allowing for model validation and refinement. This brings us to some history. The story of meteor infrasound really begins here, with the Tunguska event in 1908. A massive object, likely an asteroid or maybe even a comet, exploded in the atmosphere over a remote region of Siberia. It flattened a large swath of forest. But for a very long time, it was a mystery because there was no impact crater, and it was difficult to investigate because it happened over a very remote area. One of the key pieces of evidence came from this, an early infrasound recording from a barometer in England. Many kilometers away, which showed a clear atmospheric pressure wave. Tunguska was the first powerful demonstration that these events could be detected at very long ranges, even globally. Fast forward to the Cold War. During this time, a global network of infrasound sensors was established for geopolitical reasons. But infrasound, being a passive monitoring technology, just listened to everything. As a wonderful secondary benefit, this network also recorded powerful atmospheric events, including many fireballs. Of those, 10 major events are well documented, and their records have been declassified, digitized, and reanalyzed. And this data set is a critical statistical anchor point now as it precedes our modern digital observations. The map on the left shows the locations of these 10 events, and the image on the right shows signal, the actual data recorded on a rotating drum. This is top and middle. And the raw signal is top with all of the markings, and the lower is corrected for the curved pen arc of the recording. It's a bit of a personal note, but this was the very first project I've ever worked on in the field of infrasound, painstakingly digitizing and analyzing these old records, and we got like truly an amazing data set. And then came the modern wake-up call, Chelyabinsk. In February 2013, a 20-meter asteroid entered the atmosphere at a shallow angle, as we can see it in the photo here, generating a powerful shock wave that swept across the landscape below. It was a globally viewed event, captured by countless dashcams, and its blast waves shattered windows. The event also produced loud, audible sonic booms. The shockwave damaged thousands of buildings or broke like windows, and we can see that in photos here, and injured over 1,500 people. Critically, This asteroid came at us from the direction of the sun, making it completely invisible to our ground-based telescopes that scan the night sky. We never saw it coming. And it demonstrated that even moderately sized object can pose a significant threat. So as you can see, studying natural meteors is challenging because they're so unpredictable. And this is where controlled experiments come in. Sample return capsules, or SRCs, associated with space missions are the perfect proxy for an actual meteoroid because they have known parameters. They allow us to study different parts of their flight and are, in essence, repeatable scientific experiments that allow us to test and calibrate our models in a way we never could with a random meteor. Since the end of the Apollo era, there have been only a handful of these opportunities. The first was Genesis capsule that landed in 2004. It was detected by a single infrasound array. Then came Stardust in 2006. After that, two Japanese missions, Hayabusa 1 and Hayabusa 2, they both returned samples, but those landed in Australia. That means that the next major opportunity to study a capsule reentry over the US was the OSIRIS-REx mission in 2023. This was a monumental effort by NASA, the mission itself. It was sent to the near-Earth asteroid Bennu. Bennu is a small carbon-rich asteroid, and it's relevant because it's a time capsule from the early solar system, holding clues about the origins of life. The spacecraft collected a sample and returned it to Earth. The re-entry capsule followed a long hypersonic path, as shown in the map here, across the western US. This was a massive opportunity, so we teamed up with over a dozen institutions to bring out as many geophysical instruments as possible to capture the signals. Now, given this very long trajectory, we had to be very strategic about where to install our instruments. There are three important points in the flight we wanted to capture. First, the high altitude region where the capsule begins to generate a shock wave. This is also where it becomes luminous. Second, the point of maximum heating, which should produce the strongest signals. That was over Eureka, Nevada. And the third point, lower down, where it experiences maximum dynamic pressure closer to the end of the trajectory. That would enable us to see how the signal evolves as a function of its path. However, that first high altitude point was over an extremely rugged and difficult to reach area, so it was not feasible to instrument it due to cost and logistics. Pulling this off was a massive logistical challenge involving a huge team. Here you can see the NASA recovery team with the capsule after it landed. We're not affiliated with NASA, but I wanted to show you this photo just to give you a sense of the physical size of the capsule we were studying as it traveled on its journey through the atmosphere. So we had to figure out where to place hundreds of instruments, manage costs, get permits to deploy on public and private land, and coordinate a huge team of people in the field. So this map shows our strategy. We set up dense networks of sensors in two main regions, so-called West region, close to Nevada. In Nevada, close to Eureka Airport and at Eureka Airport. This was to capture the high altitude peak heating phase of the reentry. And so-called East region in Utah, so it was on the state line, Utah and Nevada, to capture the lower altitude phase where the capsule experienced maximum dynamic pressure. We also had sensors from different teams further out, which we call distal region, where instruments were already positioned and we were hoping to see the signals as far as 200-300 kilometers away, and in fact we did. When it comes to the Sandia National Laboratories team, we deployed a number of different instruments. These also include balloons, so we had infrasound sensors on balloons. But for tonight's talk, I'm going to specifically discuss the results from our 39 portable infrasound sensors. These are shown with circles on the map. And we placed them in these dense lines because we wanted to capture signals from different parts of the trajectory. So we wanted to see the signal beneath the trajectory and also as it changes as a function of distance from the trajectory. So this arrangement allowed us to study the evolution of infrasound signature. And I have to say, this is kind of a side note, the entry itself was amazing. A number of us were stationed in Eureka, Nevada, and we were at the airport during re-entry. Because the capsule was so high and so tiny and just zoomed across the sky, I wasn't actually able to see it. But a few minutes after it passed, I did hear a distinct double sonic boom, like a deep thump thump. And it was an incredible experience to hear that audible part that we worked so hard to capture in the inaudible spectrum. So that was really amazing experience. Anyways, the deployment worked absolutely beautifully. These plots are called spectrograms. They show frequency versus time, and that bright vertical line you see on each plot is unmistakable signal of the OSIRIS-REx shockwave arriving at 2 of our stations. So a perfect detection. Here is what we've done with the data. So with that data in hand, we could then do the really cool science. What was so amazing about this experiment was that each of our stations detected the signal from a different part of the capsule's trajectory. This figure shows all possible acoustic rays that could have reached one of the stations from the trajectory. And through our analysis, we were able to correlate our actual detection to a specific source point along that path, indicated here with the red star. And that gave us an unprecedented high-resolution look at the shockwave along its flight. And here's some more examples of these ray tracing results. And then when we looked at the actual waveforms, we saw exactly what theory predicted. The signal recorded from higher altitude portion of the flight, like what we see on the top, starting with, say, station T1, had lower amplitudes and longer, more drawn-out periods. In contrast, signals from the lower altitude portion, like the one on the very bottom shown from C7, so that was closer to Utah-Nevada state line, these were much stronger with higher amplitudes and shorter periods. We could pretty much see the effect of the capsule descending through the atmosphere in our data. And this is the plot that ties it all together. Every point here represents a detection at one of our stations. So you can see 2 beautiful distinct clusters. One is associated with signals at Eureka Airport and around that region, and the other one is in Utah or along Utah-Nevada state line. And this corresponds to one in Nevada, corresponds to region of peak heating, and over Utah, maximum dynamic pressure. So the reddish-orange cluster on the left shows high amplitude, short period signals from the low altitude, high pressure region. I probably should have reversed axes because on a map, Nevada is on the left or west and Utah is east, but this is reversed. The blue-green cluster on the right shows the lower amplitude associated with signals received at Eureka Airport. So this is a direct observational link between an object's entry dynamics and the infrasound signals it produces. So what does this all mean in the bigger picture? Well, this research has quite broad implications. For entry physics, it provides a perfect controlled benchmark to refine our understanding of shockwave behavior. For planetary defense, by better understanding the link between infrasound and energy, then we can more accurately assess the threat posed by natural impactors like asteroids. Think of Chelyabinsk. And it also helps us study atmospheric dynamics using these events as sound sources to probe the structure of our own atmosphere. And with the growing challenge of space debris, understanding reentries is more critical than ever for managing our orbital environment safely. So, to summarize our journey tonight, we've seen that infrasound is a powerful tool for studying high energy events. And we've learned how historical events like Tunguska and Chelyabinsk, combined with controlled experiments like OSIRIS-REx, have built our understanding of these phenomena. Then we've seen that simple metrics of signal period and amplitude can tell us a detailed story about objects' final fiery moments. And finally, the incredible success of the OSIRIS-REx campaign provide us a blueprint, not just for future work here on Earth, but potentially for listening to meteors on other worlds with atmospheres, like Mars. And last but not least, I have to admit, science at this scale is never a solo effort. An enormous project like this is only possible thanks to the hard work of dozens of people. So on behalf of all the participants in this field campaign, I want to gratefully acknowledge the commissioners and therefore airport staff at Eureka, in Eureka County, the DeMel family, the Nevada Highway Patrol, the people of Eureka, and the Bureau of Land Management in both Nevada and Utah, who were all instrumental in the success of our field campaign. Also, shout out to DITRA for funding this research and making it possible, and for making it possible to do really cool and very important science. And finally, I want to thank Laura May and the LA Astronomical Society one more time for having me. And most of all, thank you all for your time and your attention this evening. And I'd be happy to take any questions you might have.
Thank you very much. That was really cool. If I may, I would like to actually get the first question in there. What is the primary difference between your ground-based infrasound detectors and the stuff that's used for seismology? Like, and how is it difficult to parse geological events versus the stuff you're getting in the atmosphere?
That's actually a very, very fantastic question, and it does invoke a longer answer, but I will try to keep it very concise. You're right. Seismic sensors being coupled to the ground are meant to detect ground motion. But if we have an atmospheric event, that atmospheric event, if it produces a shock wave, can couple into the ground and produce ground motion as a result. So we call that air-to-ground coupled waves, and we've seen it from events like OSIRIS-REx, Stardust mission as well, and we've seen it with other meteor events, especially those that are quite energetic. Seismic sensors don't give us enough detail, sensitivity that is, as infrasound sensors, but they are quite instrumental in detection of air-to-ground coupled waves.
Thank you. All right,
You're welcome.
Anyone? All right. We got Mr. Dinner Party over here. He's going to invite you to dinner. That's what's going to happen.
Hi, thank you so much for your presentation. That was fabulous. I'm wondering what your main concerns were the day of the reentry, like, or, as you were lying awake the previous night, like what was most likely to go wrong?
That is a fantastic question. And now I can say things that were really worrisome at that time. And none of us did really wanted to vocalize it because it was like, we just wanted to have the signals and everything to go the right way. One of the main concerns that we originally had was local noise. So Eureka has quite active mining industry, and there was quite a bit of local noise from that activity. Also, Eureka Airport was situated close to the road, and we were certainly concerned with road noise. So we have asked the Nevada Highway Patrol if they could assist us with that, so we can have like really calm calm background environment. But only after the re-entry did we find out that NASA had about 24-hour window to abort the re-entry. So they could have, if anything went wrong, they could have continued the mission and come for another sweep. So we were very happy that everything did happen the way it did, and the capsule safely landed and brought the samples because this was truly massive undertaking with many people and many different teams.
Question: can you do similar scientific work on rockets that are taking off, in addition to the ones that are coming down?
Yeah, actually, there has been quite a bit of work associated with that. We at Sandia, we actually have quite active balloon infrasound campaigns, and it's actually very cool that you asked that question because we did detect on balloon sensors Starship explosion, one that occurred a couple of years ago. And there are many research groups that actually do specifically work with infrasound coming from rockets and from many other sources. So it's a very rich research field when it comes to that.
Oh, I got another one here.
Thank you for doing this lecture. I'm sorry if this was in one of your slides, but what was the speed of the reentry compared to like the typical meteoroid?
Perfect question. Thank you for asking that. No, it wasn't in the slide, and I should have put it there. Maybe I did in the table. But anyways, the speed of the capsule was about 12 kilometers per second. That was entry. The slowest meteoroids are about 11.2 kilometers per second. Stardust remains the fastest artificial re-entry at 12.6 kilometers per second. So this one was very, very fast, up there with Stardust.
So you're studying infrasound from meteors and things crashing into the atmosphere. So can you use this data to estimate, like, what's the total number of meteors or what's their mass that are intersecting the Earth that we don't see? Well, that's basically my question. Can you tell us what's raining down from space that we don't see?
Excellent question. So the benefit of infrasound is definitely global coverage. We can see things at very large distances, or we can detect things at very large distances, and we can sometimes triangulate where they are. But difficulty with infrasound many times is we can't conclusively determine whether infrasound was caused by, let's say, a bolide, or maybe some other type of explosion, such as mining activity or volcanic eruption. It can be very, very challenging. And that is mainly because infrasound from bolides comes in a certain frequency range that overlaps other natural events. So sometimes it's very difficult to tell what it is. And if we don't have detections by several different arrays to pinpoint location, it also makes it challenging because you see the signal, you can perhaps say direction where it's coming from, but you can't really pinpoint how far it is. So it could be a weak signal from closer in, or could be a strong signal from further away. Sometimes that's very challenging to determine.
All right, I can't see the Zoom questions. Roman, can you shout one out?
I don't see any questions online yet, but I do have one.
Oh, there is a, yeah, go ahead. There is actually a question in Zoom, but I will answer it next.
Oh, if you can read it. Okay, yeah, one just came in. Go ahead, just go ahead and read it.
Yeah, the question is it like login signature as they, I can see this.
As they do in submarines.
As they do in submarines. Yes, we log signatures. And as I said, they come from different sources, but in many cases, we can't really tell what it is. There so many things generate infrasound. One of the best ways to determine how much stuff we have coming in terms of meteors is all sky cameras. And there are several groups, or actually many groups, that are specifically working on that problem. And there is now a global meteor network that is a consortium of many institutions with a goal to capture as many meteors as possible with highest accuracy as possible.
Yeah, Dr. Silber, I have a question. Thanks for the excellent talk. So when you listed some opportunities to study these reentries, I guess I was questioning what about all the manned reentries back from the shuttle program and the Dragon and all that. Then you mentioned, the speeds at which you're looking for, and the manned reentries are probably too slow for you. So I just want to kind of ask that question. What about other opportunities from low Earth orbit reentries, including some commercial capsules that are kind of more or less routinely re-enter over Australia and things like that?
Yeah, that's an excellent question. And we can readily detect infrasound from slower stuff, such as deorbiting. That has been done quite frequently. Very tragic event of Columbia space shuttle was also captured on seismic and infrasound, something we never want to see. Very unfortunate. But one major difference between orbital debris and re-entering spacecraft from interplanetary space is indeed, as you mentioned, speed. So these re-entries allow us to study the speed regime that is associated with slow meteoroids. So they're proxies. But when it comes to orbital debris, yes. If we have a planned deorbiting and we know where it's going to land, it makes things a little bit easier. But sometimes things are more stochastic. They're also meant to, if deorbiting is controlled, they're meant to go into a very remote region, which makes it, again, challenging to record infrasound. There was a recent case of a Chinese space station, or Chinese station, however you want to call it, in 2024 that re-entered over California. That was kind of unplanned, but it was captured by a number of seismic sensors that was analyzed by my colleague Ben Fernando over at Johns Hopkins. So there are a number of instances that have been recorded of space debris.
Thank you.
You're welcome.
All right, anyone else here? Oh, I see it. I see it.
Hi, thank you so much for that talk. It was wonderful. I have a question about the data sets themselves. When you were so excited about the data set that was like your first project,
yeah,
and how rewarding that was to be kind of cleaning that data, or I'm not sure, sort of like making it readable, or I'm curious to know like who has access to these data sets. Like, do they live within individual organizations, and off of who has access to the data sets, have there ever been any like surprising applications of the data that have like excited you, or sort of like taken you by surprise, that like someone accessing the data for something that maybe you didn't think this kind of data would necessarily be useful for?
That's a great question. So back in the day, we're talking about 15, 20 years ago, cloud storage wasn't a thing. So it was mainly whoever had data back then, you put it somewhere, record it, and it just sits there. So over the years, there has been effort to make data available as much as possible. And I'm really happy that you mentioned this historical data set because we recently published it. It is fully accessible to the scientific community. It is hosted by Harvard Dataverse, and we have data paper that came out of it. I would be happy to share that with you. Recently, we also published another data set of regional meteors that were detected over the period of about 6 years in southwestern Ontario. That's also publicly available for any application that goes beyond the original data analysis, because these data sets, especially if they're well constrained, are extremely rich. Rich in a sense that if you do one publication or focus on one aspect of the study, certainly there is much more to do, especially now when we have more capabilities to do machine learning and more technologically advanced studies. So I am always for data access, and from our OSIRIS work, once when we're done with analysis, we intend to publish the data set. And when you ask about interesting applications, one really cool observation that we've seen, and I was super excited, actually, the whole team, not only myself. I mentioned we had balloons deployed during OSIRIS-REx reentry. So we detected a signal that came from the capsule. It was captured on the balloon, and then it hit the ground and reflected back up. And it was again detected by the balloon. So that was super cool.
Awesome. I saw one more from Everardo. He was talking about if you found anything interesting in the noise that you're collecting, about maybe the Earth having a harmonic.
Well, noise is very interesting, and there are always interesting things to see in the noise. That is a whole another topic in itself. But again, when it comes to infrasound, sometimes, especially in populated areas, or if you're flying balloon with infrasound payload over populated areas, there is so much noise. It could be from just anthropogenic activity to storms, winds, anything. And in many cases, while we do find noise as interesting as coherent signals, it does require additional work and additional analysis, because it's way more challenging to disentangle where things are coming from.
Oh, we got one more.
Thank you so much for the talk. It was awesome.
Thank
I was
you.
wondering, how sensitive are the microphones that you're using to pick up the infrasound? And like, is it possible for hobbyists to also like set up their own microphones? Is that like within a reasonable price range? And also, if
Fantastic
you're like
question.
oh, thank
So-
you. And if I guess, sorry, one really quick follow-up just before I give the mic back. Like, if you live in a city, like, would you be able to hear anything that's actually interesting, or would it just be drowned out by the noise that you're talking about?
So to
Sorry.
answer your first question, yes, as a citizen scientist, you can have affordable infrasound sensors. There are quite a few university-led groups that are aiming at building small, portable, low-powered sensors. And as a matter of fact, these that we used in OSIRIS-REx deployment, these were developed by Boise University, and they're very small, portable. Basically, you can put them in your hands and take them anywhere. They require low power. Raspberry Shake and Boom, those sensors are also quite affordable. A lot of people have them, and they're pretty much available to purchase to anyone. Also, you can use your own cell phone as an infrasound sensor. The University of Hawaii Infrasound Group, they have developed Vox app, Red Vox app for the cell phone that basically turns your cell phone into the receiver. And a really cool thing about that is it was used during OSIRIS-REx deployment and it detected strong signals. So I hope that answers your question. And your follow-on question, if you had your own sensor in your own backyard, would you be able to record anything? Just think of lightnings, storm, any sort of impulsive activity would certainly generate infrasound noise. Even if you're looking at any sort of rubble type of noise, the advantage of you recording something that's nearby is certainly attenuation factor. You can detect it when it's closer. Further away you go, it's more difficult. So more commercial type of sensors, they're more spread out and less likely to capture these transient events at larger distances because of attenuation.
I think I saw a couple more questions come through the chat, but I can't see them. Can you?
Okay, so one question from online was, is it possible that interstellar non-humans could be detected now that information is being declassified by this technology in the science community? In other words, did you hear the aliens land? Just tell us.
Well, I don't know.
Okay, another question.
I am not qualified to answer that question.
That's unfortunate. We were hoping. Another question was, if you study infrasound coming from the ocean, that may be due to the splashdown of meteorites.
That's actually a very good question. Probably when it comes to splashdown, the question is how much sound would that produce, what is the frequency content, and how quickly would it attenuate? I would presume that sonic boom from the meteoroid itself would be a much larger infrasonic source than the splash.
Okay. Anything else from anyone, anywhere? Going once? Going twice? Okay. Thank you, Dr. Silber. That was awesome.
Thank you.
I'm going to be downloading that app for sure. I have filters for that. I don't want the good part. Okay, let us move on to our next item, which would be our club governance. Now, this happens every once in a while that we have cause to change our club bylaws. And we're going to be addressing two topics today that are pretty functional. One of them is actually something that probably should have been addressed a little while ago. And that is we are hoping to make a revision so that the board of directors alone can award honorary life membership to a nominee without requiring a vote of the general membership, to where basically we have like a Hunger Games style vote on whether we think someone's done enough for us or not to garner a honorary life membership. Now, to be clear, the people who usually get these things are members that have been in the club for a number of decades, and they're doing the thing for long enough that we feel that they can just be part of us forever. And then the second part has to do with how we're handling the Lockwood 5 construction project, in a way just to pretty much just change our accounting, to give the board the ability to create a separate fund aside from the general fund, so that we can keep track of where what money is supposed to go where. This allows members that do choose to make a donation to be guaranteed that it goes in the pot that they want it to go to, and that it doesn't get turned into something that they don't want it to turn into. So, with all that excitement, the changes exist in these two places, and we're going to vote on them a la carte. Goes like this. Article 1, Section 9, regarding honorary life membership is being changed to those regular, senior, or youth members who, for outstanding services to the society, shall be nominated by a member in good standing and approved by a vote of the majority of the board of directors. They shall have and retain for life the rights and privileges conferred by these bylaws without the payment of annual dues and, if desired, or receive complimentary copies of the Griffith Observer. The honorary life membership will also include immediate family members who reside in the same household as the honorary life member. I make a motion to approve these changes to Article 1 in the bylaws. All in favor? Any opposed? I think we can. All right. We will accept that change. Can we hear you? Actually, let me be sure. Can we hear you guys in Zoom? Somebody say something.
Yeah, you're coming across.
We can hear you. Okay, very good. Okay, the second bit, going into Article 12, we are changing it to call audit and finances rather than just, I believe it was called audit before. We are going to be changing section 4, 5, 6, and 7. Not huge individual things. Section 4 is changed to a general fund will be used to finance ongoing operations such as postage, office supplies, and paying for utilities and the maintenance of LAS facilities, which is what our general fund is currently. Section 5 will say the board of directors may vote to establish one or more separate funds and associated bank accounts to provide monies for specific projects or programs. These monies will be separate from the general fund. Section 6 will say project-specific monies may be used to address an emergency only after a vote of 2/3 of the board of directors and the general membership is informed of the nature of the emergency and the justification for using project-specific monies. This notice will be communicated electronically for comments at least 1 week before the project-specific monies are used for the emergency. Section 7 will say, if project-specific monies are used for an emergency per Section 6, the board must make a good faith effort to restore the monies as circumstances and finances permit. I make a motion to approve these changes to Article 12 in the bylaws. All in favor? Opposed? Look at all these thumbs. Is that thumbs for all in favor, I'm assuming? Okay. All right. Good job, everybody. We governed. Thank you.
Keith,
I
we
feel
have
like I
one
need one of those
opposition
powdered
online.
wigs for this. No powdered wig for me. Okay, great.
Keith,
Now let's get into our
let me jump in
announcement.
here. We
Oh,
have
sure.
one
Go ahead.
opposition online
Oh, I'm sorry.
for the
Who do we
record.
got?
Well, I'm not sure it matters. We just want to state it for the record.
Okay, and we had one opposition. Okay, fair enough. Thanks for pointing that out. All right, now on to our announcements. We have a number of things to announce. One is going to be particularly important to those wanting to partake in our dark sky site. We now officially have a warming hut up there with new furniture that is clean, smells good, looks great, and it'll keep you. It's small. What used to be what was called we're calling the FKA new bathroom, which is now the currently known warming hut and data center. It has a refrigerator in it, which we probably won't need for the winter, but we've used it once so far, and it will be something that you'll be really happy about at Lockwood when it starts to get frigid. When it gets cold, you'll like it. Okay, the next thing worth noting, I don't know how many of us noticed, but the robotic observatory took a little swim, but thanks to the heroics of Roman, it is back in operation. So if you wish to explore the cosmos from the comfort of your own warming hut at home, you can continue to do that. So that's fantastic. Next up is something that I've been working on. As you may know, we have had for a long time a discount at Woodland Hills Camera and Telescope. And more recently, we've gotten discounts with ZWO. But I'm super stoked to announce that we now have that with Agena Astro as well. It's a 3% discount, which doesn't seem like a lot. However, we also get the club gets 2%. We'll call it a kickback that will go into the general fund. So I know a lot of us shop at Agena Astro anyway, so this is a way to get half of your tax covered. I will be putting on the groups IO the instructions on how to do this. It's a coupon code plus a cool little suffix you have to put on the end so that you can feel special for shopping in a great way. This is probably the most important of the announcements. This Saturday, October 25th, at this very site, the Griffith Park Star Party is going to be curtailed to 8 telescopes during the day and 6 telescopes at night. If you wish to participate in this star party, please reach out to Dave Yackerson at music88 at sbcglobal.net so you can so that you can register to be a telescope presenter, a participant. There's no grass. You'll note we're having the grassy shoes that we had before, so we're going to be like we did it twice already. We're doing it again. All right, so that's the thing. Another big announcement is that we have Science Night coming up on Sunday, October 26th. This is one of our highlights of the year at Garvey Ranch Observatory. We have kids from all over Los Angeles, a lot of fun stuff. We're participating with NASA and the Planetary Society, I think the Columbia Science Center, and a few others. It's a lot of fun to come do it. There'll be a rocket launch, some people wearing funny clothes, and it's a really good time. If you've been wondering where that hat that Keith is wearing came from, they are there are a couple still available. This has these are going to go into the fund that you just voted for to raise money for the Lockwood Development Fund. Okay, that's all that fun stuff. And now comes to my favorite part of the general meeting, the Good Heavens section, where I'd like to call out a member that I feel has needs a spotlight shown on them for their works within the club. And this month, I'd like to call out Ed Dempsey, who almost none of you have met because he lives in Denver. But you've seen his work because he's the one that runs the club Instagram account. So he's kind of an unsung hero, but he's the one posting cool LAS AP images taken by you guys. And he also shares both upcoming club events, and he also shows pictures recapping the completed ones as well. He's also really great at feeding the algorithm to help LAS increase its profile. Of late, he has had a pretty viral post regarding the Comet A6 Lemon, which got 5,000 likes and 8,000 shares. And thanks largely to his efforts, the club just topped 31,000 followers, which is pretty crazy. If you have no clue what I'm talking about, just trust me, that's pretty cool, especially for a science group. So thank you very much, Ed. You're a boss. I think it's time for some door prizes. I have 2. If you wish to write, if you wish to see your words published, you want to get published? A lot of writers want to get published. You can get published. Write something cool to go to bulletin@laas.org. You don't have to be as smart as Dr. Silber or Roman or Tim. You just have to be interesting. And you know, this club is about a lot of different things. A lot of my favorite things to read about are more experiential. You know, if you had what your association with Astro has been, what you've learned, the people that you've met, the friends you've made along the way, that's great too. Or something like technique-wise, you can get technical, you can be funny. All right, here, win a door.
Keith, there was a question online before we go to raffles.
Go ahead.
Whether the 100-inch night is still on for October 24th.
It is, and I will be there.
Can I mention about this Friday's outreach?
Oh, I'm going to be getting.
Okay, fine. Okay, so to the door prize. Here we go. Get your tickets out. Is there anybody who did not receive a ticket? Okay, we're good. Here we go. We're giving away 2 prizes here and 2 online, if I'm correct. And you'll keep track of who won? Or somebody needs to keep track and write it down with their names for the, especially if the, oh, Justin's good? All right.
Yep.
Justin, you ready?
Oh, I'm so ready for these lasers.
Okay, buddy. Thank you so much. You're the man. Okay, here we go. First one is 8335 406. You won. All right, Laura. There you go. What did she get? I think it's the first. We're going to give a. What did she get for the? Is it the
We're making it all even. Everybody gets $50 gift certificate.
$50 gift certificate from this our store, from the online store. 5406. Yes? Okay. And the last one over here would be is 8335. Yeah, I figured that. Okay. The last numbers are 416. We got a winner. Oh, congratulations. Okay, so yeah, come on down and let Justin know who you are. Thank you. So, right.
you get a $50 gift certificate. Do you want to express your joy?
I just want to thank Jeff for the dinner party, and when I got here, he swapped tickets with me. So thank you. Just want to shout out Jeff, great dinner party host. What prize do you want me to get? Okay. Oh, take the gift card.
You want the gift card? Yeah. He wants a gift card. Okay. All right, online folk.
All right, we have 2 winners online. We ready?
Bring it.
All right, first is Nady de Oliveira.
Hey.
All right.
Won again.
Congratulations. And the second winner is Everardo Hernandez. Congratulations.
All right. Congratulations, all. Choose your gifts wisely. Okay. So now is our upcoming events. We have a busy schedule of things coming. This is kind of a weird general meeting because it's later in the year. So I'll be announcing stuff this month and next month. And so you're going to be hearing some of these things again next month also, just because that's how I want to do it. And I'm the president. So, right. Okay, so the next general meeting here is going to be November 10th in this place, in this area. The next Griffith Park Star Party is, as we mentioned, is the limited one coming up this Saturday on October 25th. We have a lot of outreaches coming up. The next Silver Lake one this Thursday is a big one. We're going to have the band, and it's going to be a whole thing. If you haven't done it yet, it's awesome. Come out, bring your telescope, or don't, just bring your vibes. That's great too. We have a Santa Monica outreach on November 15th. Then we have a host of school outreaches. We have one coming up this Friday in Arcadia, 1024. We need it. Okay, so we need more telescopes out there. Then next month we have on 1114 in Altadena, 1128 in Monrovia, 1119 in Azusa, and then 1121 in Santa Fe Springs. So, that's enough ample time. Go do it. There's no more family nights this year. Sad face. But we have a dark sky night coming up on 11/22, so you can take advantage of the warming hut I was talking about earlier. We have probably what's going to be the last star party at Mount Wilson of the year on 11/14. If you haven't done that, that's really awesome because it's outreach, but the sky is actually pretty great. Yeah? Yeah. Yes, all this, I'm basically reading this off the club calendar. Yeah. I am reading these, this is off the private one. So I'm making it public, so freaky. That spills over. It goes, what, the public star party? Okay, 15th, sorry, not the 14th. We have, and then if you want to take part in our club governance, if you really got some blood in the water voting on this one, you can sit in on a board meeting on 11/5. And then the Lockwood Committee meeting preceding that will be on 11/3, and that's where we talk about cool stuff like bathrooms and telescopes and stuff like that. We'll get into that. We'll do soon for that. Yep. Okay. Any other questions? Oh, let's talk. We'll get a little bit into the calendar. On the club website, there is a calendar that you can go and find. That's our public-facing one that now feature it. We don't put the school outreaches on there for safety reasons, but we do have the Lockwood stuff on there. You will find. I wonder if it's still here. I don't see it anymore. On the if you go onto the groups IO, there's a subgroup that's called LAS Calendar, and then if you go to the calendar portion in the calendar subgroup, you'll find the whole LAS calendar there. And if you are on Night Sky Network, our calendar is there as well. If you would like, there are Google calendars and iCals that link to all of the stuff that I'm talking about right here. And if you want that link, reach out to me at president@laas.org, and I will send those to you. It's basically just a relay of what the Groups IO one is, but it's accurate, and that's what I use. I think it's great, except for that thing about the 15th. Okay, I think we're done. Thank you. Oh, and thank you for everybody who came to Astro Trip. That was so fun. I can't believe some of you guys showed up here. It's too late now. I'm going to write about it. You're going to hear about it endlessly. That's true.